If you've ever wondered how you might use CFD to analyze a nuclear reactor, then this is the talk for you. I'm going to be doing something quite different today. I'm not going to be presenting a lecture series or a podcast. I'm actually going to be showcasing some of the real work that I delivered to analyze a nuclear reactor using CFD. Now, this work is particularly exciting because it is carried out as part of the UK government-funded nuclear thermal hydraulics program, and the work itself is published on the Institute of Mechanical Engineers website. So not only can you follow along and listen to this talk, but you can actually go and download and look at the work for yourself and use it as part of your own analysis and CFD best practice. To get access to the work, I've left a link in the description of the video, and if you just click and follow the link, it will take you to the project website here on the Institute of Mechanical Engineers. And the website briefly describes the project, which is a set of 6 technical volumes, which you can see here, which contain information which describe the current best practice in thermal hydraulics analysis of nuclear reactors. And these are meant to be reference volumes or theses which you could use and refer to in your own work if you're an engineer analysing a nuclear reactor. So we've got 6 different technical volumes, and you see they cover common topics like convection, radiation, conjugate heat transfer, natural convection, and also specific volumes for liquid metals and molten salts for different types of primary coolants. And each of these technical volumes, if you click on them, link to detailed PDF documents, like the one you can see here on the screen for volume 2. And these volumes contain lots of detailed information for exactly how you would carry out these analyses if you were carrying them out for yourselves as part of a CFD analysis of a next generation reactor design. Now, in addition to these technical volumes which show you how to analyze a nuclear reactor, we also have at the end 4 case studies. You can see here study A, B, C and D, which actually showcase these methods applied to realistic scenarios that may occur in the development of a modern nuclear reactor design, for example. And the study I'm going to be taking you through is study C, which is one that I was particularly involved with. So if you're on the website, you can just click the link on study C here, and that will load up the PDF document which describes all of the work that I was a part of. And in this talk today, I'm going to be going through this document in some detail to showcase some of the exciting work that I did on that case study. Now, before jumping into the work and the analysis in any detail and actually showing you the details of the reactor design, it's worth just pointing out a few bits before we jump in. And the first one being, if you read these reports and you want to use any of the information in your own work, you can reference them, and the appropriate reference is in the preface on page 4, which you can see here. So feel free to read the reports and you can reference them and use the information in your own work. And it's also worth noting that the documents themselves are distributed under the Creative Commons license, and you can always click the link to follow that if you want details of the license and what it allows you to do. But broadly speaking, what the license allows you to do is to copy and redistribute and share the material as you want, but of course you can't do this for commercial purposes, and you have to leave attribution to the source. So always make sure you provide a reference if you're going to be using this information at all. But this is the fantastic thing about these documents and about this project, is that normally it's quite difficult to find information about how you might design a nuclear system or a nuclear reactor design, and that's for good reason. That kind of information is very sensitive and is often very difficult to come by. And the key feature of this project that allows us to distribute this information under the Creative Commons license and on the Institute of Mechanical Engineers website, and the important thing to remember is that when going through this analysis of study C of a reactor design, it's important to remember that all of the information, the figures and the numbers are fictitious. They are based upon best estimates of what one might think a nuclear reactor of this type might look like and how it might operate. But of course, all of the dimensions, the values, the temperatures, the flow rates are completely fictitious. And so you wouldn't want to use any of the data or this information because it is all completely fictitious. And so you couldn't use it. And it's that key feature of the project that allows us to share and distribute this information. Now, overall, the project was developed with a number of partners, which you can see here on the screen. We've got Westinghouse, EDF Energy, Rolls-Royce, and some universities as well. So the information that you'll see, particularly for the details of reactor design and the case studies, these are more examples of how you might design a scenario like this if it were to occur. But of course, the values themselves are fictitious. So a reactor with a diameter of 10 meters, for example, is completely fictitious. It could be 9 meters or it could be 10.5. Those values aren't the important thing. The true value of these analyses is they show you how you might undergo the analysis of a nuclear reactor if you were to have one. And that's some of the exciting material that I'm going to be going through today. Now, in particular, I'm going to be looking at Study C, as this is the study that I was most involved with. And this study involves looking at the decay heat removal from a nuclear reactor that is cooled by liquid lead. So the primary coolant that surrounds the reactor is not pressurized water or CO2, it's liquid lead. And this is an interesting example of one of the Generation 4 new nuclear reactor designs that are being proposed to improve the future of our nuclear energy supply. So if you're interested in that kind of analysis, stay tuned. I'm going to be going through Study C here to show you some of the work that I did to showcase how you might analyze a nuclear reactor with a lead primary coolant. Okay, so the first thing I'm going to do is talk a little bit about the reactor itself and how it physically operates. And then when we've got an idea of how the reactor works, we can start thinking about how we might analyze that using CFD. So in the report, I'm just going to flick down through the first few pages, past the preface, past the contents page and the introduction section, and I'm going to have a look at this diagram on page 10, because this diagram explains quite nicely the overall layout and design of the primary circuit of the reactor. We can use this to understand how it works. So there are a lot of different labels on this diagram, and perhaps the easiest place to start by thinking about the core. Now, the core that you can see I've got here is right in the middle. We've got an active core region in red and then a lower core region in grey. And roughly speaking, what we want to think about is this is the region in the reactor where the nuclear fission process is actually going to be taking place. So we've got this in this region of the reactor, and the active core bit, that refers to the bit which is actually active and producing the heat. And then we've got this lower core region underneath where we've got a lot of the supporting structures and other components just underneath it. So when thinking about this reactor and actually how it works, we start in the active core, and while the reactor's operating, this active core region is going to be giving off heat and radiation. But the most important thing for our analysis that we care about is actually the heat. And we're doing the CFD analysis, and we'd like to know, where does this heat go and how is it transported around the reactor? So what happens is that we've got our coolant, our primary coolant, which is passing up through the core. And you can see this with the blue arrows here on the diagram. And the coolant's going to be coming in the bottom of the core and passing around the various fuel assemblies and components that are in the core. And as it does so, it's of course going to be absorbing some of the heat that's given off the fuel rods in the reactor core. And then that primary coolant is then going to pass into this region above the core, which you can see here in the salmon pink. And it's now a lot hotter. And these kind of grey regions, which you can see there in the middle of the diagram, these are the control rod drive lines. So these are where the control rods are inserted into the bottom of the core, and this is where the machinery will be for controlling those control rods. But our primary coolant can flow around in between those control rods, and what it's going to do is once it's passed up through the core, it's going to move upwards as it's driven up from below, and then it's going to pass out in the radial direction. So because this is a slice through the middle of the reactor, it's going to pass out in the radial direction through a primary heat exchanger. And we don't really need to know what the details are of this heat exchanger for the moment. All that we're going to know is that our hot coolant is going to go in through the heat exchanger, and that heat is going to be removed and pass into a secondary coolant, which is then going to transport the heat away to a steam turbine, which is going to be driving and creating the electricity that our reactor produces. But back to the primary coolant, what we're interested in is once our coolant leaves the heat exchanger, it's now cooled down. A lot of the heat that it absorbed from the core has now been given off to the secondary coolant. The primary coolant is then going to be driven down, so it's going to go, I've got this dotted line in round the back to show that this is a circumferential large pool around the outside of the reactor. And that coolant is then going to be drawn into a pump, so just like a standard pump, but this one is driving the fluid back down from the top of the reactor back underneath into the bottom of the core again. So you can see that this entire circuit creates a complete loop. So we've got our coolant, it's driven, pushed down through the pump into the bottom of the core, where it then passes around the fuel assemblies and the fuel rods and absorbs the heat from the nuclear reaction. And then it's going to pass out through the heat exchanger, give off that heat to the secondary coolant, which is then going to go and drive a steam turbine, and then the coolant is driven back down again into the bottom of the core. So this is the overall method that our primary circuit coolant is going to be circulating around the core in a continuous fashion. And what have we got around this core component of the reactor? Well, the entire thing is contained in a shell, which we're calling here the reactor vessel. So this is a large metallic shell that contains all of the primary circuit fluid within it. And there's in this reactor design at least, there's a gap between that, and then there's a secondary containment vessel outside that primary containment vessel. So if there was a leak for some reason, then all of this primary circuit fluid is still contained within this shell of the primary circuit reactor unit itself. So this is just a nice little overview about the reactor unit itself and how everything is contained. And at the moment we haven't really looked in any detail. We've just seen how the fluid is going to be moving through that reactor and how it's going to be continuously circulating to be continuously transporting that heat away from our active core region. Now, in this particular design, one of the interesting features that we've got around it is you can see there's this large blue region around the outside. And what this blue region represents for this fictitious design is that the entire reactor core region, which you can see here, this shell, is sitting in a large pool of water, kind of like a swimming pool. So imagine that this is a sort of an 8-10 meter wide, so very large cylindrical vessel, and the whole thing is sitting in a really large swimming pool. And why would we do this? Why do we want the entire thing to be sitting in a swimming pool? We haven't really heard or seen of this before. Why are we doing it? Well, the reason for this comes in when we have a loss of power to the reactor itself. Now, this is an issue which can happen to any power plant, not just nuclear power stations. But if there's a loss of power, of course, what will happen is that many of the components in the reactor will cease to function because they need electricity to drive them. So if you think of the power lines which are providing electricity to the nuclear power station, if there's a power cut for some reason or an uncontrolled blackout, what will happen first of all is that the pump, which needs electricity to drive and push the fluid around the reactor, will slowly spool down and shut down. And the other thing that's going to happen is this primary heat exchanger, which is transporting heat away from the reactor. There'll be another secondary circuit which drives a secondary coolant around to transport that heat away from the primary heat exchanger. And that fluid will no longer be pumped around the circuit because its pump will also have shut down if there's a loss of power. So what that means is that not only will our fluid not be circulating around the reactor itself, but also the heat, which was primarily been taken away by the primary heat exchanger, will no longer be taken away. And this is clearly a bit of a problem for the reactor design, and is something that we want to design for. And there are a number of different ways we could account for this fault event. But how this particular reactor works is the entire unit is sitting in a large swimming pool. So what that will mean is that the reactor itself, when that coolant is no longer circulating around the core to cool it, the entire reactor is going to start heating up. And what's going to happen is the heat's not being transported away by the primary heat exchanger. So what's going to happen is that heat is actually going to make its way out through the sides, through the reactor vessel and the guard vessel, into the swimming pool. You can imagine that then this whole thing is sitting in a swimming pool. The swimming pool is going to start steaming and start boiling eventually, as all of this heat from the nuclear reactor is going to be leaking out into the swimming pool. And what will then happen, of course, is that the large swimming pool, it takes a lot of energy to boil water, but eventually that water will slowly boil down and boil away as the reactor itself cools down, because the nuclear reaction will have stopped. And that's really the scenario that we're wanting to look at with this model, is that what's going to happen when there is a loss of power and that water starts slowly boiling around the outside of the reactor. And the thing that we're mostly interested in, because we could quite easily calculate how much energy is going to be put out into the swimming pool and how long it's going to take to boil down, but the thing we're actually interested in is what happens inside the reactor, because it's going to start getting hot, and we want to know how hot does it get, are there any components that might overheat, and what happens to the temperature gradients in here. Are there any regions which are locally very hot and other regions which are locally very cool? And also, what's going to happen to this primary coolant that's circulating around the reactor? Because even though it's not driven by a pump anymore, it's still hot, and all of my fluid mechanics engineers will know, of course, that once you're heating up a fluid, you're going to have buoyancy effects. And so the primary coolant is going to want to drive itself in some manner around the reactor under its buoyancy. As you're heating it up, it's going to move upwards. And even at a first glance here in the reactor, we can see that because of the way it's designed, when this active core region is undergoing radioactive decay and it's putting heat into the primary coolant, that coolant's going to be heated up and it's going to want to move up because of its buoyancy. And then as it moves around the reactor, the outer edge of the reactor is being cooled by the swimming pool, and that's going to cool down the fluid. And so as it cools, it's then going to want to move back down to the bottom of the reactor because of its now negative buoyancy. And so we can see just by looking at the reactor that even with a loss of power, there may be some mechanism for the coolant to circulate by itself. It won't be, of course, as strong as if it was driven by a pump. And we want to see, how is it circulating, and does it circulate well, or are there any issues we might need to worry about? So that's a quick overview of the reactor itself, and what I'm going to dive into now is talking about the CFD analysis itself and how we might set this up. Imagine you were the engineer who were given the task as part of a team of analysing and setting up an analysis of this reactor. How might you do it? That's what I'm going to look at next. Okay, so now what I'm going to do is just flick forward in the report, view from slide 10 to slide 24. And if you're following along, of course, by yourself, feel free to just flick through to page 24 so you can have a look at the diagrams for yourself. Now, there's a nice figure here on slide 24 which really illustrates how we're going to be analysing the reactor and actually what conditions we're interested in. Now, it's very important for us to think about actually what conditions specifically we're interested in with the reactor, because you can imagine that during an event like a loss of power, a lot of different things are going to be happening all at the same time throughout the entire plant. So not just the reactor, many different systems will be activating, turning off, turning on, and some of those systems will kick in immediately and other systems will take time. And clearly an entire nuclear power plant is a very complex system, and we want to home in on the exact issue that we're interested in, that we're going to analyse with this specific model. Those other systems we'd analyse separately. And these plots, which you can see here on page 24, are actually quite interesting to understand what happens to the reactor itself and the primary circuit after there's that initial loss of power. And the first plot I want you to look at is this one in the top left, which shows the core power and how the core power, or the heat that's given off the core, how that varies after the fault event. And you can see that at time equals 0, that's when our electricity cuts off. You can imagine all the lights will shut off as the electricity goes down. Before then, you can see that the core power, so the amount of heat the core is giving out, is at roughly 100%. And then what happens is that the moment that the power goes out, the electricity goes out, the control rods are inserted into the core, and that stops the process of nuclear fission, or at least reduces it to a very low rate. And of course, what then happens is that the heat given off by the core drops rapidly in the first. It drops at an extremely steep rate, which you can't quite see from the diagram here. But the important thing is that that heat drops down, and it comes to around 1%, at least for this model. We've assumed around 1% of what its initial thermal power was it was giving off when it was undergoing nuclear fission. And that's very important to understand with the nuclear reactor, that even though the control rods have dropped in, nuclear fission is essentially stopped, the reactor itself is still hot. That block of nuclear material that we've got in there is still giving off heat, and that's because, of course, we have radioactive decay. So there are a number of different isotopes in the core which are still hot, and they're undergoing radioactive decay, and that heat is still coming out of the core. And this is the heat that we actually have to deal with when we're thinking about the fault that the nuclear reactor undergoes, because if you were to leave that heat uncontrolled, of course, things would continue to heat up, and that's where we could get problems with the reactor. And what we can see is that, after a few hours, we're getting radioactive decay now, and of course that heat will slowly decrease over time, and as many of you will know, of course, that will be an exponential decay for the radioactive decay heat there. But for us as engineers, 1% of the initial power is still a lot of thermal energy that's coming out of the reactor, and this is the heat we need to deal with. So this is what the core is doing. We can think the core is no longer really hot, it's dropped down and it's a lot cooler now, but it's still giving off quite a lot of heat. And what's going to be happening to the lead temperature, so the lead being the coolant temperature around the primary circuit? Well, of course, what's going to happen is that before the loss of power, before the electricity and the lights go out, our lead temperature is pretty hot, and in this case it happens to be something over 400 degrees. And then, of course, as soon as the power goes out and the pump stops working, we're now not getting that convective cooling anymore. So the pump is slowly spooling down. You can imagine you've got a big heavy pump, it's spinning very fast, and the power goes out and that pump will slowly start spooling down until it completely stops. And as the pump slows down, the circulating fluid is slowing down, so it's not pulling off as much heat from the reactor. And so the temperature of the lead starts to increase. And you can see that there in that first region on the plot there. And now what we've got is we've got two competing effects going on, because our core is cooling down, the radioactive decay heat from the core is cooling down, but also we're now not circulating our fluid as fast as we were before because the pump's gone. And we then reach this point, we reach a kind of peak in the lead temperature where the pump is no longer pushing the fluid around. The fluid is being driven around by natural convection, its buoyancy. As it absorbs heat from the core, it moves up and then goes around the reactor and cools, and it's then drawn back into the bottom. And that gives us this kind of near maximum point where the lead temperature reaches its highest value. And of course, if we continue into the future, the reactor decay heat and many of the other systems continue to cool down. But you can imagine that for the engineers who are designing this reactor, one of the things you'd be interested in is, what is this peak temperature? How hot do things get? And is there a local hotspot? Do we exceed the melting temperature of some of the components, for example? That's something we'd really want to worry about. And this is kind of the condition that we're really, really most interested in, because we've still got a lot of decay heat coming off the core, but our lead temperature has now slowed down and is barely circulating at all. And The other interesting thing to think about under this fault condition is what's happening to the swimming pool, what's happening to the water level around the reactor. And initially, we've got a water level that's 7 or 8 meters deep. It's very deep. That's going to be roughly 2 or 3 times the depth of a conventional Olympic swimming pool. It's a very deep pool, which you can see here. And after the initial loss of power, of course, what happens is the heat exchanger will slowly stop absorbing the heat. And what happens is, you can imagine this water pool, this swimming pool, which is maybe sitting at 30 or 40 degrees. What it will first do is it will absorb the heat that's given off the reactor, and that will heat the water up slowly to its boiling temperature. And when it gets near boiling and it starts steaming, what will then happen is the water will evaporate and be drawn away as steam, and that results in the water level in the swimming pool starting to drop. And you can see that in the little diagram here, that the blue line, the water level is slowly going to start dropping around the reactor. And you may worry and think, well, what happens when the swimming pool boils away completely? What happens when there's no swimming pool left? Well, under those conditions, we are going to get natural circulation of air. So this vessel will just heat whatever air happened to be in the swimming pool. You can imagine your swimming pool, wherever, if you've ever been swimming before, if that swimming pool boils away all the way down to the bottom, all the air that was in that swimming pool room is now going to be heated up and will draw heat away from the reactor. And of course, air is much less effective at removing heat than boiling water, but by this stage we can see that maybe after 5 or 6 days, so it takes a long time to boil away a swimming pool. A swimming pool has a lot of water in it, but by this point the reactor decay heat is also going to be a lot lower as well. So the heat that's given off the nuclear reactor isn't as much, so we don't actually need as much cooling to remove that away. So for this model, as you can see, it's quite a complex system, and actually if we wanted to simulate this entire event with water boiling away and slowly being reduced and switching to air cooling, we'd actually need a model to run for 5 or 6 days. And for many of you who carry out CFD analyses yourself, you know that it's not going to be possible, even with perhaps the best modern computers, to have a large CFD model and to run that for 6 days of simulated time. It's too long. The model will take years and years and years to run. So instead, what we decided to do in this analysis is look at the most critical point, or the most dangerous point that we're interested in. We pick a specific point in this analysis quite early on, so after the electricity goes off, when the power is still very high, the core is still very hot, giving off a lot of heat, and the lead temperature has gone up. We've got a really hot lead pool because the pump has spooled down, but the water level has started to drop. And you can imagine the water level may be sort of halfway down the outside of the reactor. And the reason this condition is interesting is because the rate of cooling that we're going to get above the water level is going to be a lot lower than below the water level. You can imagine this is sitting in a really cool bath below where the water is, but above, these regions of the reactor are going to get really hot. And so you might naturally be concerned, maybe these components near the top, or maybe the shell, the reactor vessel itself, might start overheating at the top first. So this is the condition we're going to look at with the CFD model. We're looking at a very small snapshot in time, and we may be able to do a steady state analysis or a small local transient to look at a specific condition. And we have to do that, of course, because we can't run a full 6-day CFD model with this. So now we've probably got a good idea of what our reactor is, how it works, how the water and the coolant and things are going to be working over the course of a transient. What I want to look at next, which is going to be the bit that I imagine most of you are interested in, is how exactly do you model the components within the reactor itself? What are we going to do for the heat exchanger, the core, the pump? How are we actually going to build a model? How are we going to sit down with some CAD package and some mesh generating software and a CFD code? How are we going to put this all together? What is the magic? That's going to be in the next section of this talk. So first things first, let's skip back a few pages to page 21 in the report. And what you'll see on this page is a top-down view of the geometry of the reactor. And what you can see, of course, is it's cylindrical, and you can see that a number of the components are repeated around the circumference of the reactor. And we've actually got 6 primary heat exchangers here, and we've also got 6 pumps. And looking at the pattern of the control rods in the middle of the reactor as well, you can see that these also form a regular pattern. And this is really useful for us as analysts because straight away we can identify that there's actually some periodicity to the reactor design. In this case, we've got that 60-degree section, which is periodic. And what that means is that for our analysis, we can just analyze directly this 60-degree section of the reactor and then apply appropriate periodic boundary conditions on the side to account for the effect of the other components in there. And this is, of course, going to cut down the size of our model, make the model a lot easier to run, and also a lot easier for us to manage as well when we set it up. And there are a few, of course, limitations of this approach with the periodic section, particularly near the middle of the reactor, but those are discussed a bit more in the report. So the first thing that we've done here when looking at how we're going to set up a model and how to analyze this is just looking at the geometry and identifying there's a periodic section here, and I can use this to simplify the geometry that I have to make and make things a lot easier for myself. The next thing that we can do as well is thinking about the extent of our model and how far the model extends into the outside world. And one thing we could do with this scenario is we've got the water pool or the swimming pool around the reactor, and of course to calculate the heat that's been absorbed by the water pool and drawn off the reactor, we could include the water pool in our model and make a computational mesh for the water pool and predict and calculate the convective currents within the water and in the air above that. But instead we can actually do something quite clever, and you can see the dotted red line here on the figure. We can limit the extent of our computational model that we're going to construct just up to the edge of the reactor outer shell. And instead of modeling the water pool explicitly in the mesh, we can apply appropriate boundary conditions to model the effect of that water and the air on the model. So you can think one way that we could do this perhaps is with a really high heat transfer coefficient on the region below the water to model the effect of the water boiling and being heated up by the reactor heat, and then a separate maybe heat transfer coefficient above the water level to model the effect of the air. And that, for this model at least, is a really efficient way of us limiting the extent of our model. Again, we're reducing its size, so it's going to run a lot quicker and be easier for us to manage as well, because we don't have this large excess region around the outside. So those are the first 2 simplifications we can make when modelling this reactor, and it's very useful in all of your CFD analyses as well to take some time to think about what are the extent of my domain, how far does it truly extend, and can I do anything clever with symmetry boundaries or periodic boundaries when I'm analysing my model. Now let's go ahead and look at some of the individual components themselves within the model. And the first thing I want to talk to you about is about the fuel assemblies. So what we want to do now is first think about the core region in the reactor. So that's the region right in the middle where nuclear fission is undergoing and where we'll be getting our radioactive decay heat from. Now, some of you may not have come across fuel assemblies before, but a quick Google image search shows exactly what we're talking about. Now, nuclear fuel generally is arranged into fuel rods, so very long, thin rods that have a diameter of maybe only a few millimeters. You can see these in the images, and those long, thin fuel rods that contain the uranium and the nuclear fuel are arranged into a fuel assembly, where a load of these rods are collected together, either in the form of a hexagon or a square. These are probably the most popular shapes, and you can see this is the fuel assemblies. This is the assembly of all the fuel rods, and the fuel rods are kept packed together by spacer grids and various supporting structures to keep those rods at an equal distance along the length of the fuel assembly. And this fuel assembly may be a meter or 2 in length, And the reason that, one of the main reasons that nuclear fuel is arranged like this, of course, is simply due to the surface area to volume ratio. So there's a lot of surface area of fuel that's surrounded by coolant so that we can draw off as much of that heat from nuclear fission into the coolant. Whereas, of course, if we had our nuclear material all as a big block, then only the outer surface of that big block would be able to remove heat. But for us, we've got our fuel rods are arranged into fuel assemblies, and for this particular reactor we've got hexagonal fuel assemblies. We haven't got a square assembly. And for us, when we're building our model, this gives us a problem of scale when we're setting up a CFD model. And the reason for that is, you may have noticed that the reactor itself is 8 to 10 meters in diameter. It's maybe 5 meters high. It's really large. But then the fuel rods themselves are only a few millimeters in diameter. And this is a real problem primarily for meshing and time step control, because we would need to reduce the size of our mesh all the way down to the size of those fuel rods and have several cells across the fuel rods themselves if we wanted to include that in the mesh. And somehow we would also need to extend our mesh and our time step all the way up to the size of the full reactor, which would be quite difficult to do. So what we have to do is we have to pick the scale that we're interested in for this model. And for this particular model, we care about the overall primary circuit reactor itself. We're interested in those effects at the scale of order 1 meter, for example, rather than a few millimeters. And so what we need to do is to come up with an appropriate representation of the fuel rods and the fuel assemblies. And there are a number of ways you can do this. And what you can see here on slide 29 is this is just an example of a fuel assembly pattern. So you can imagine those fuel assemblies, they're hexagons and they're all stacked together in a very careful pattern. And for our CFD model, one thing we could do is we could either mesh and resolve the individual fuel assemblies themselves, which are maybe 10 to 20 centimeters in width, which is still a lot larger than the fuel rods, but is still a lot smaller than the overall reactor. We could include the overall fuel assemblies in our reactor, or we could just model the core as regions where heat is coming from. And the representation that we want here is we just want to make sure our core is putting the right amount of heat into the primary coolant, and also providing the right amount of resistance to the flow as well. Because you can imagine that the primary coolant, the lead, is coming in through the bottom of one of these fuel assemblies, and then as it's moving around all of the fuel rods, of course, the frictional force is going to be opposing that motion, and we need to make sure that the effect of that friction, or the pressure drop as the flow moves through those fuel assemblies, is accounted for in our model. And we could either do this with rings of effective material that gives off the right amount of heat and frictional loss, or we could model these as individual hexagons that give off the right amount of heat and pressure drop. And for this model, we decided to go with the hexagonal prism representation, which above anything is probably a bit more exciting as well for you at home to model. So we're going to see this hexagonal prism representation of the fuel assemblies. And you can see on the slide here they're coloured in different colours, and the reason for that is we're going to be getting more heat coming off these fuel assemblies in the middle of the core when we're undergoing radioactive decay than the fuel assemblies around the outside. And the fuel assemblies around the outside, these are called shield assemblies in this case, because they shield a lot of the other components in the reactor from the ionizing radiation that's being given off from the fuel isotopes as it undergoes radioactive decay. So that's why those are in grey and the others are in red. So we've chosen this representation of the hexagonal prisms for our fuel assembly, and of course you can read a lot more for the justification in the report if you're interested in, but for this talk I'm just interested in giving you the understanding. And what we need to think about now is how we can arrange that fuel assembly pattern into our periodic model. And this is a bit of a head scratcher. You might have to think about this for a while, because of course this pattern is for the whole reactor, and in our model we're only going to take a sixth of that. and we want to make sure that the edges of our sixth are periodic, so that the heat and the flow going off one edge of the periodic section is equal to the heat and flow coming off the other edge. And there's two ways we could do that. We could either just draw our periodic boundary straight through the middle of those fuel assemblies, but that's only really allowable in this model because our pattern happens to be periodic itself. We happen to have that hexagonal pattern of the fuel assembly layout. Whereas if we had a different fuel assembly pattern where we had squares, for example, you could imagine that if you're drawing that periodic boundary through the squares, the pattern might not be periodic, and so you may have to come up with a more elaborate periodic boundary. But luckily we're not going to do that today. We're just looking at this 60-degree section of our fuel assemblies in the middle of the reactor. And so what do we do about the heat and the losses from those regions? Well, what we're going to do, for those of you who've done a bit of CFD analysis before, you're probably used to the concept of using a porous media or a porous zone to represent this region. And this is particularly useful for us in this model because it means primarily that it allows us to look at this larger scale, so we don't have to resolve the individual fuel assemblies. And this diagram on page 30 is a nice way of understanding what's going on here. You can see the image on the left. I've got two hexagonal fuel assemblies which are close together, and there's a region between the fuel assemblies where we've got the primary coolant is flowing between the assemblies. So the primary coolant flows around the individual fuel rods in the fuel assembly, but it also flows between the fuel assemblies themselves. You can see that in the blue region here. And so what we're going to do for the core is actually come up with two different porous media regions. And you can see that here in the diagram, that the first thing we're going to do is model the entire fuel assembly there as just a hexagonal block of porous material. And in that porous material, we can of course apply loss coefficients, so we get the right pressure drop across the fuel assembly, and also apply a volumetric heat source, so we get the same heat coming into our coolant that represents the heat that would be given off these fuel rods here. And then what we also do, the really interesting bit, is we come up with another porous media model for the flow that's passing between the fuel assemblies here. And this porous media will account for the frictional losses from the walls of the hexagonal fuel assemblies. So this is kind of a conceptualization of how we're going to build a CFD model of the core of a nuclear reactor. And I just want you to get a good idea of what's going on here, because of course you can read the report if you want details of how the loss coefficients are calculated. There's details of that in the model here with values, and also details of how we calculate the coefficients for the porous media model for the flow that's passing between the fuel assemblies. But the main thing I want you to take away is this is how you might model a reactor core at this sort of resolution. You could, of course, if you were looking at an even more intricate CFD model, you could mesh the entire fuel assembly itself. You could mesh the rods, and you could mesh the fluid around the rods. And this is something which is done in one of the other case studies, which are also on the IMechE website, and maybe I'll take you through one of those later. But I'm really hoping you're getting a good grasp of how you can model a nuclear reactor core in CFD from this report. Now, the other interesting things are, how do we model some of the other components? What do we do with the heat exchanger and the pump? And if we flick to slide 38, we can have a good idea of how we're going to model the pump. And what you can see here as part of the sketch, of course, is this is a sketch of the wedge model that we have in the CFD. We've got the 60-degree periodic section. And for the pump itself, at this stage, we may know what the pump looks like. We may know the number of blades, how they're rotating, what their rotational speed is, how much blockage there is. But the difficulty with this model, of course, is remember that we're considering a blackout event where there's a loss of electricity. The electricity to the site has gone down, and so the pump is now actually stationary. So in this pump housing, we may have some impeller blades, we may have some rotors and some stators, but this pump is stationary now. And all it's going to do is provide a resistance to the natural convection driven flow that's moving around the pools. And so what we decide to do is, like many of the other components at this scale, is just model this as another porous zone. And again, what we do there is provide a resistance that would provide the same level of resistance if we'd actually meshed the rotor blades and the impeller blades themselves. This is really useful, of course, because it means our mesh can be a lot smaller and we don't need to mesh our rotor blades and we don't need to create a sliding mesh zone or anything. We can just put a porous zone in there. And we can do a similar thing for the heat exchanger as well. With heat exchanger designs can be extremely complicated. You can have lots of different tubes and plates to increase the efficiency of heat transfer. But what we decide to do in this model is, because we're not interested in the heat exchanger, we just model it as a block of porous material which provides the right amount of resistance. And here's a nice little diagram as well of some of the components at the top of the reactor. And you've got the hot pool in the middle where we've got the lead, which of course comes up above the core, it's hot, and then it pushes itself out through the heat exchanger, which is of course beneath the surface here, cools down, and then it's in this upper cold pool of where it's going to flow down again. So another sort of nice diagram to explain what's happening here. And there are also some details here as well if you're interested about how we model the outside of the outside surface with the water pool and the water level. And broadly the way we do that is by using empirical correlations for natural convection around a vertical cylinder to get the right amount of heat and the right heat transfer coefficient to apply on the outer surface of the reactor. So if you look at these kind of systems yourself and you're interested in, you can find detail of the maths and how we set up the model in this section of the report as well. Now, the next thing I'm going to jump onto is looking at the mesh, because I know many of you CFD engineers will be interested in. So now we've worked out how to model a nuclear reactor, how do we actually mesh it? It's going to be a very complex and difficult meshing exercise. How do we actually do it? That's what I'm going to look at in the next section. So now let's move on to talk about meshing. We're on slide 40 at the moment. If we just flick through the report down to page 46, there's a nice overview of the mesh and what we're going to be creating here. Now, the most important thing to notice about how you would mesh this CFD model of the reactor itself is that we've actually generated meshes for the fluid regions and the solid regions as well. So there are mesh for the lead pools, the porous media regions for the fuel assemblies, but also the solid components as well. So this reactor vessel shell, guard vessel shell, and also the gap, the air gap between the reactor vessel and the guard vessel. We've meshed all of those regions. So this is a conjugate heat transfer mesh. And the reason this is particularly important for this case is because we're going to be getting conduction along the thickness of these metallic surfaces. Even though they're only, it's only maybe a few centimeters thick, conduction from one pool into the other is going to be extremely important for interpreting the results. And we're going to see that when we look at the results a bit later. And so there are a lot of different regions that need meshes in here. And of course, at first glance, this would look like a very daunting meshing problem. You've got a lot of different areas, and how do you make sure that your mesh is high quality and isn't going to cause divergence, and how do you make sure that it's sufficient quality for an accurate result in all of these regions. And what I'm going to do is just show you the mesh in a few of the different regions and then talk about how exactly I created it. So the first region of the mesh to look at is just this region here in the gap between the inner reactor vessel shell and the outer reactor vessel shell, or the guard vessel as it's called here. And there will be fluid in this gap. It could either be an air gap or it could be an inert gas. In this case we've got argon, so there's an inert gas in there. And at first glance this region is actually going to be extremely important because the reactor vessel will of course be hot, it's going to be heated by the lead, and then this guard vessel is going to be cooled by the water and the air on the outside. So there's going to be a significant temperature gradient across this cavity, and we're likely to get circulating flow in here, and we're also going to get radiative heat transfer across it as well. So what I've got here is, you can see there's a really high quality structured mesh all the way across, and we've got the thin cells right on the wall there. And those very thin cells, for those of you who've done CFD meshing before, we'd really like to get a low Y+. If we can get a Y+ of around 1, that would be perfect. And the reason for that, of course, is we're going to have the thermal boundary layers are going to be extremely important for getting the recirculating fluid right in this region. So we've got a high quality mesh, and you can see that the solid components, so the reactor vessel and the guard vessel, are also meshed. But we don't need as high of a resolution for these components because they are metallic, and so the temperature profile is going to be relatively constant across them. They are good conductors. If we flick down to the next page, we can see some more interesting regions of the mesh down in the bottom of the reactor around the core. And if I look at this image on page 47, you can see on the outside here, I've got the orange region for the argon gap, I've got the guard vessel, the reactor vessel, and then this purple region here. This is the lower pool of lead. So this is the cool region of lead that circulates around the bottom of the core before the lead is drawn up into the reactor core. And the mesh structure around here is quite interesting. Of course, it would be very difficult to generate a fully structured mesh of this region with only hexahedral cells because it has a complex shape. And so what I've got is I've got quite a thick layer of inflation layers on the surface of the reactor vessel, and then there's a transition region into a hex core, which you can see here. All of the cells in the bulk of the pool are perfect cubes of a certain size, and this is really good and really useful for the CFD analysis if you can generate a mesh of this quality, because of course these cells have perfect quality, so they're not going to have large non-orthogonality or skewness, so it's going to be speeding up the solver because these cells have a perfect shape, but also it's going to give us a nice accurate solution as well, because part of the solution we expect in here is that for our temperature to be relatively stratified. We're expecting the reactor to be quite hot near the top and quite cool near the bottom, and so actually with relatively quiescent flow in the pool. And so actually having these square and quadrilateral cells aligned with where the temperature gradients are and where we think the flow is, it's going to give a high quality solution. In the same way that we can see here with the inflation layers, what we're expecting the flow to be cooled by the wall and then to be driven down the wall by negative buoyancy. And so the inflation layers are roughly aligned with where the flow is going. And of course, this transition region between the inflation layers and the hex core, you can never avoid that. You always have to have that. But we'll look at the solution a bit later and see that this doesn't appear to have any effect on the flow solution. It's got quite a complex mesh structure in there, and an even more complex mesh structure out the top of the core as well, where we've got the fuel assemblies, and once again, we've got the same hex core approach. We've got these perfect cube cells in the hot pool, and we've got the inflation layers again running down the outside of this containment shell that contains the hot pool. And that's particularly useful, of course, because once again, this metallic region is connected to the cold pool. So this is going to be cooling the fluid in here, and we expect to have a thermal boundary layer, a flow running down this wall, and so having the inflation layers there is going to be very important. And perhaps the most exciting region is the mesh of the core and the fuel assembly porous regions. So what you can see here, just in the overview sketch, is I've taken away that fluid region above the core, and so you can now really see the mesh that we've got for those fuel assembly porous regions. You can see these are all perfect hexagonal prisms, which are just extruded through the length of the core, and we've got that perfect 60-degree periodic section. So we haven't got the full fuel assembly pattern, we've just got the 60-degree section. And if we zoom in on the top of the mesh, what you can see is we've got the hexagonal fuel assembly porous regions. Remember, we're going to be having the pressure drop here, and we're also going to be having this as the heat source. This is where the heat source is coming into the model. And then we've got this thin region between the fuel assemblies, which is called the inter-wrapper region here, and that's where we're going to have flow bypassing the fuel assemblies and coming up through the core. And we haven't got a very fine mesh here. We've only got 3 cells across the gap, and the reason for that is we're not resolving the boundary layers that are going to be developing on the inside of those walls, because instead we're applying the resistance as a porous loss. And this is a really cool mesh structure which is actually perfectly replicated, so you can see that the edges of the periodic boundaries, those mesh cells correspond exactly with the corresponding cells on the other edge of the periodic boundary. And that can be quite tricky to do in your mesh generator, and often takes a lot of practice and often looking at the manuals to work out how to do it. For those of you who are interested, this particular mesh was generated in ANSYR, and ANSYR is particularly good at doing things like periodic boundaries, which is one of the reasons for choosing it. And you can also see the edge of the mesh structure here, right near the core barrel. You can see the fuel assemblies go right the way up here, and then there's another region of flow, a bypass flow, which can flow around the outside of the core completely. We've also got that in the mesh structure there as well. Okay, so now we finished looking at the meshing, let's dive in and look at the analysis itself. What I'm going to do is flick through to page 60 in the report, and that's where we're going to start looking at some results. Now what you'll see on page 60 is we've got a lovely contour plot of temperature, and we've got a vector plot of velocity. And these plots are taken on a slice right through the middle of our periodic section, which you can see there in a nice salmon pink colour. And if we start by looking at the temperature plot, we can see quite a lot of information about what's actually happening to the primary circuit lead in the reactor. And this is the core region, which you can see there just with the dashed box, and we're looking at the lead itself that's flowing around the loop. And if we look in the region above the core, of course this is going to be the hottest region of the primary circuit, because the lead has just been heated up by the core and the temperature is reaching sort of 740 to 750 degrees. It's really, really hot. And what's happening to the temperature and the flow in this pool here? Well, remember of course that this region is a lot colder. So this region of lead is a lot cooler, and the outside of the reactor is very cold because it's connected to the water pool on the outside. And so what that means is that heat of course will be conducted through the wall of the core barrel, and this will act to cool this inner wall of the hot pool. So we've got the hot flow coming out of the core and it's being cooled by this wall. So what that means is that the hottest flow is going to be driven up the middle and then out and around and then cooled as it passes back down the wall. And we can see this in the velocity vector plot, which you can see here. The lead is being driven up the middle of the core, kind of like a plume that's coming out the top of the reactor. And then as it passes out, it's then cooled by the core barrel, and then it flows back down the outside and into the heat exchanger, which you can see here. And the velocity vectors tell us that actually under these natural circulation conditions, where there's no pump driving the flow's not moving very fast. The maximum flow is only 20 centimeters per second. So 20 centimeters is about that much. So the flow is moving by about that much every second. That's the maximum. And throughout the rest of the pools, the flow is moving only a few millimeters per second. So these blue regions, the flow is almost quiescent. It's hardly moving at all. That's what's happening in the hot pool. That's quite interesting. If we now move and have a look at this lower cold pool here, so the flow is very hot, it's being continuously cooled by the outer surface of the reactor, and then by the time it reaches the cold pool, its temperature is now down at about 720 degrees, and it's quite interesting to see that throughout the entire pool the temperature is relatively constant. It's only varying by a few degrees throughout the pool. And the reason for this, of course, is that our primary coolant is lead. We're not using pressurized water or pressurized CO2 or anything in this reactor. We're using liquid lead. Of course, liquid lead is a metal, so it's really conductive. And what that means is that the temperature variation throughout the reactor is actually quite small. The whole thing is almost at a constant temperature. There are only a few degrees of temperature difference throughout the pools. But what we see here is that in the pool, as we move down, and we go back down under the core, the temperature is dropping as we expect. This lead is being continuously cooled by the outer surface, and its temperature is dropping down from 730 to 726, 710, and then all of a sudden as we get to the bottom of the core, the temperature rapidly drops off and it gets below 690. So the whole thing is almost at a relatively constant temperature, except for this region right at the bottom of the reactor. And this is one of the things we wanted to look for, and was the reason why we were doing the analysis. We wanted to see, are there any hot spots or are there any cold spots? And a hot spot and a cold spot are just as bad, because it's the temperature gradient on the structural components, like that shell of the reactor. If we have a large temperature gradient, that's going to induce some high thermal stresses in those components, which would be bad for the stability and safety of the reactor itself. But what's actually happening in this lower cold pool? This is the really interesting bit, is that this outer wall of the reactor here, this of course is connected by the gap to the outer surface, which is then cooled by the water pool. And so this region is really cold. It's got a cool boundary that's cooling it down. And what that does is it locally cools the flow, and that reduces the density of the lead. So the lead gets cooler and its density changes, it gets us a lot heavier, and then that drives the lead along the surface of the reactor vessel here. We have a sort of a negative density current. You can think of this working in the opposite way to a balloon. When fluid is heated, it wants to move upwards. When fluid is cool, it wants to move downwards. And so the flow is locally moving down the outside of the wall there. And this is maybe 15 centimeters per second, so the flow is moving relatively fast along the wall compared to the rest of the pool, where this large pool, which is maybe a meter or two in radius, is only moving, it's just gently swirling around at a few millimeters per second. And then right at the wall, you've got this rapid flow, which is driving down the outside, driving flow up into the core. But what's happening at the bottom here? What's happening at the bottom? Why do we have this region of low temperature here? Why is the temperature really cool? Well, this is actually quite an interesting case, and it's to do with buoyancy and stable buoyancy and unstable buoyancy. And we actually have to think quite carefully about what's happening in this region here. And what you want to think about is that the temperature of this surface is going to be very cold. This is sitting in a pool of relatively cool water, and then you've got the hot core above it. So what happens is, as the flow is driven down, it's cooled continuously by the surface. When it reaches the bottom, it's cooled even more. And that means its density changes and the flow wants to move down. The buoyancy is trying to drive the flow down here. And what that means is that the flow struggles to move up into the core because it's cooled, which is pulling it down. Whereas the rest of the flow jets over the top and is drawn up into the core. So this ends up being a region of relatively stratified flow, where that flow is going to be cool and it's just going to sit there, and the rest of the flow in the pool is very hot. And that's going to create some interesting temperature gradients on that reactor vessel shell. And you can see this in the velocity vector plot here as well, where the flow jets down along the outer surface of that reactor vessel, continuously being cooled, and then it's drawn up into the core, but this region right at the bottom is just sitting there and it's hardly moving at all. So those are some really interesting results that we can pull out from this model. And if you flick through the report, you can see a lot more results. There's a load of analysis in here which is really interesting to look at. Got a comparison of steady state and transient analyses, also looking at what happens in the other pools in the reactors, what happens as the flow comes out of the heat exchanger into the mixing pool, where does it go and what does it do. You can see that there on slide 6 on page 67. This is the flow going through the heat exchanger, and we have a small region of reversed flow in the heat exchanger, which is quite interesting. And then a further analysis of this stratified region at the bottom of the reactor here. And if you were doing this CFD analysis, this is something you might want to pass back to the design team to inform them that perhaps this is a region of the reactor that we would be concerned about in the event of a station blackout or a loss of power. Now, for those of you who are interested in liquid metals and actually doing the CFD in a bit more detail, another thing which I've got here is looking at actually that flow that moves along the outer surface of the lower cold pool in a bit more detail, looking at the development of the boundary layer and the wall functions and the wall modeling and the level of resolution in the CFD that we've got there. And for those of you who are interested, I'd highly advise reading this section of the report. It starts on about page 69. It goes into a lot of detail about how the wall functions and the wall models work and whether they're going to be sufficient there for capturing the flow of the liquid metal. So that brings me to the end of my quick review of case study C of the nuclear thermal hydraulics project. I'm really hoping in that quick review that you learned quite a bit about nuclear reactor modelling and how you might undergo it for yourself if you were to undertake an analysis like that, and also use some of the information that you've learned perhaps to improve some of the modelling of your own analysis. And I'd really encourage you at this stage that if you liked the work, go ahead, look at the report and look at the reports for the other case studies and the technical volumes. Download them for yourself, have a look and see if you can learn even more than you've got from this brief talk. And mostly let me know in the comment section, did you enjoy this? Did you find it extremely useful? Would you either like me perhaps to go into a bit more detail in this for this particular case study, because there was a lot of detail which I had to glance over and I couldn't fit into this talk? And would you perhaps be interested in some of the other case studies in the technical volumes? Because I'm considering looking at those as well, because there's a wealth of information and useful content in there for CFD engineers and engineers as a whole. But really it's over to you. Let me know. Did you find this useful? Would you like to see more? I really look forward to hearing from you in the comments section. And once again, thank you all so much for continuing to support the channel. I really do appreciate your support, and I'll see you in the next video.